Okay, now we have a Joaquin. Tell us how the
Hello. Can you see me? Can you hear me well? I guess, can you hear me?
yes.
Good. Let me share. Okay. So yeah, what I'm going to be talking about today is, as Deco said, the finite element approximation theory. So essentially the finite elements from the mathematical point of view. So the main idea, so yeah, just a brief outline. We are just initially going to discuss the mathematical theory behind the finite element approximations. And essentially this consists of, okay, we're going to start thinking first in a certain domain, what kind of bounds we can put on approximations by polynomials on a certain domain. Then we're going to identify that domain with a reference triangle of our mesh to kind of get some bounds specifically for that case. Then we're gonna try to think how those bounds translate to the real triangles of our mesh. And then finally, we're gonna sum over all of those bounds for each of the triangles of our real mesh to get a global bound, or hopefully a global bound on our whole mesh. And that program is what we are going to call finite element approximation theory. And finally, we're going to do some applications briefly to the Dirichlet problem to see what kind of errors we can get when we approximate the solution to a Dirichlet problem by elements in a finite element space. So as I was saying, now more concretely, the idea is to estimate the approximation errors that we get in a finite element method. So essentially, we want to look at something like this. We have a certain function u that could be the solution to a differential equation that we're trying to solve. And we want to approximate that function by functions that live in a much smaller finite dimensional space, which is our finite element space. And we want to see how close we can get by functions on that smaller space to the true solution of our problem. So the question is, how well can we approximate u using functions in the finite element space? So that's the guiding question behind this theory. So the setting is I'm going to be calling omega to a certain bounded domain in Rn, although most of the time I will be talking about R2 actually, just for concreteness, but everything can be extended to in a straightforward manner to higher dimensions. But then our function space will be typically a subellipse space, which I'm going to briefly remind you what it is in a moment. And then u in this subellipse space will be typically the solution to some differential equation, particularly a weak formulation of differential equation, which we aim to approximate using functions in our finite element space. So just as a brief reminder, I'm sure you saw this before in the course, but it never hurts to repeat something you already know. So just to make sure we are on the same page, if we have a bounded domain on Rn, we can define the Sobolev norm in this way, which is a kind of an extension of the L2 norm that would only take this term here. But now we consider also the derivatives of the function that we are trying to calculate the norm. So essentially, the Sobolev norm is an extension of the L2 norm that takes into account also the derivatives. And given this norm, we can define the Sobolev space of order m as a completion of the functions with derivative, continuous derivative up to order m with respect to this norm. So essentially, we will consider functions here and whatever we can get, in a sense, close to by functions that live here, in a similar way that one can, for example, think of the real numbers as the completion of the rational numbers, in the sense that if I only have the rational numbers, I have sequences that they seem to cluster around certain places that they get, the points can get very close to each other, but they don't seem to go anywhere that lives in that space. So then we can just decrete new elements and say, okay, we call this the limit of these sequences, and this is what a completion is. And here we do essentially the same. But what this allows us to talk about, so when we talk about a Sobolev space, essentially we are thinking of this norm here that takes into account derivatives, and we want to be able to talk about this derivatives maybe in a more relaxed sense. But yeah, essentially what you have to keep in mind is this norm here. This is the main aspect. And on the other hand, this I am also sure that you already saw, but just as a brief reminder of what a finite element space is from the mathematical point of view. Here we are talking about a set of piecewise polynomials with respect to a given triangulation of a domain that we call this TH here, where H is the size of the mesh, which is essentially the largest diameter of any triangle in this mesh, which gives us a sense of how big one of the triangles can be. And we specify the finite element space by giving for each triangle in this triangulation a certain finite dimensional space of polynomials, right? That live on this triangle. And not only that, but also a set of what is called degrees of freedom, which is a finite set of linear functions that take these polynomials and map them to R. That's why they are linear functionals. So essentially they live in the dual space to this function space. And they have the property that they are unisolvent. What that means is that if I specify the value that a certain function in this function space takes when I evaluate the degrees of freedom on this function, right? So I apply each of the linear functionals to the functions here. They give me a certain real values. And if I determine these real values, then I determine a unique polynomial function here. So yeah, essentially, these degrees of freedom completely determine the way that we can project from the general function space to this finite element space. Why? Because these degrees of freedom determine a basis for the dual space here. So then by demanding that the projection of a function here in this space matches each of the values of this linear functional, then essentially this projection is unique, right? And so it's completely determined. And this is the usefulness that these degrees of freedom have. I forgot to say, if you have any questions, feel free to stop me and ask at any moment. So yeah, to put it in more concrete words, what I just said, think of, for example, the Lagrange finite elements, which are defined by basically the values that the polynomials take at certain nodes. So for example, for Lagrange elements of order 1, we have then linear polynomials. And as we know, any linear polynomial in 2D is completely determined by the values that it takes on 3 independent points, right? So essentially, by evaluating a polynomial in these 3 points, a linear polynomial, I know completely about which polynomial I'm talking about. So it's completely determined by these evaluation functionals, right? Same for higher order. Now, if we have polynomials of order 2, then we add more nodes, and the values that this polynomial of order 2 take on these nodes completely determine which polynomial of order 2 I'm talking about, and so on for higher order as well. We add more nodes, and in general, we gain accuracy, and we at the expense of more computational cost. But this is the general idea. Now, as I was saying, you can think of evaluating at a node as a linear functional. I am taking a function and I am producing a real value from that function by evaluating it. And I am using this evaluation to construct this space. So now if I have any function that is not necessarily a polynomial, I can project it to one of these spaces, basically by demanding that when I evaluate it on the nodes, so that when I evaluate the projection on the nodes, it has the same value as the function itself evaluated on the nodes. So basically, I am using the degrees of freedom to define how to project any function here. And this is an idea that we're going to use in a moment. So in general, then a finite element space is then assembled from each finite dimensional polynomial space on each of the triangles, right? So essentially, we have these functions that are piecewise polynomials that on the triangles of the mesh, they reduce to one of the polynomials of our finite element, let's say, shape functions. And the continuity of the functions then we enforce by requiring that the degrees of freedom match, right? So if we have 2 different triangles that share an edge or that share a vertex, then essentially we make sure that the functions are continuous by enforcing that the degrees of freedom of the function on each side essentially match, so they have the same value. So for our program of a theory of finite element approximation, what we're going to need is some kind of projection that has certain good approximation properties, and we are going to construct this. And then we are aiming to this result here called the Bramble-Hilbert lemma that will lead us to bounds like this one here. Essentially, we have our function u that's, for example, the solution to our problem, and we want to know what the distance is of this function with respect to the projection of the function to our finite element space, right? And the kind of bounds that we are going to aim for are bounds like this, where we have a constant that depends only on the domain, and then here a measure of the derivatives of the function itself at a higher order. So we're gonna see this a little bit better now. So yeah, going into the theory itself, we start with a useful result here, which is called the Poincaré inequality, which says that given a certain domain on Rn, a bounded domain, whose boundary is Lipschitz. So typically, for example, a smooth boundary or a polygonal boundary, then we know that there is a constant, a positive constant, which depends only on the domain, that guarantees that the L2 norm of a function in the subolab space of order 1 is bounded by this constant that only depends on the domain, and the L2 norm of the gradient of this. Given that this function U satisfies this condition here, that says basically that the average on the domain is equal to 0. However, this inequality also holds even if this is not the case. But for example, if U vanishes on the boundary of the domain, which is what this circle here means, or even if it vanishes on any non-empty open subset of the boundary. We're only going to see a simple one-dimensional proof of this here, just to get an idea of how it goes. So essentially, we take one function in the C1 of I, where I is a certain interval, a real interval. And we suppose, as the conditions of the theorem say, that it has 0 average on the interval. So then, since it has 0 average and it is continuous, we know that it must be 0 somewhere. It cannot be positive everywhere or negative everywhere. So essentially, we can call this place x0, this place where the function is 0. And this allows us to write a very nice relation. So if we have U now evaluated at any place x, we can write that using the fundamental theorem of integration of calculus, in this way, right? As an integral between x0 and x of the derivative. So we take the norm and square it here. And using the Cauchy-Schwarz inequality, we essentially get this bound here, where L is the length of the interval, right? So we know that this must be less than the length of the interval times the integral now of the square of the derivative. And finally, if we integrate this inequality on both sides, on one side we get the L2 norm of U, and on the square actually, and then we also take the square root. So but essentially on one side we get the L2 norm, and on the other side we get this L. So this is a constant essentially on the interval. So we only multiply by L and take the square root, and finally we get then L times the L2 norm of U prime. And this, if you remember, is the result that we were trying to prove, that the L2 norm of U could be bounded by the L2 norm of its derivative in the one-dimensional case, and where the constant C only depends on the domain. Here it's the length of the interval. So this is to get an idea of only how the proof goes, and we are going to use this Poincaré inequality now to construct the bounds that we want to construct. So now just I think you probably also saw this before, but just in case, to define some handy notation, what we call a multi-index is an n-tuple of non-negative integers, like here. And essentially, the reason that we define this thing here is to talk about derivatives of mixed derivatives of high dimension in a handy way as here. So essentially, when we say the alpha of U, where this alpha is a multi-index, what we're saying essentially is the derivative of order this alpha here, which is essentially the sum of all the elements of all the indexes of each component, let's say. So this is the total order of the derivative. And here we take the alpha 1 derivative with respect to x1 and so on, the alpha n derivative with respect to xn. So this is basically a handy way of writing a mixed derivative. And yeah, this is the main thing that we need this for. So other things that this makes more convenient is, for example, to write a polynomial in Rn. We can easily write it in this way, where x alpha now is this thing here, right? It's the product of each of the coordinates exponentiated to each of the components here of the multi-index, and each of these terms has a constant coefficient here, and we are summing over all the possible combinations of multi-index that have its order less than r, right? So we can easily write a multidimensional polynomial in this way. We can easily write also, for example, a linear differential operator of degree r in this way, where the idea is exactly the same. We have the derivative written in this way, and then we take a combination of all of these derivatives, summing over all the multi-indexes that have order less than a given degree r. And this gives us a linear differential operator of degree r. Another thing, for example, just to gain some familiarity with the notation, is we can write very easily the multidimensional Taylor expansion in this way, right? So if we have a smooth function in a neighborhood of a certain point in Rn, then we can expand it in this way here, which looks very compact, right? We have the alpha derivative here and x minus x0 to the alpha. And the remainder will be some error of other m plus 1, because here we are summing terms up to order m, right? So yeah, this is the little detour to explain this projection. And now, so the way that we are going to prove the bounds that we need for the convergence, for calculating the convergence rates. So we're going to define a useful projection, right? Which is this one that I'm going to introduce now. So we're going to call this little italic PR to the space of polynomials of degree less than r on our domain omega, right? And we are going to introduce the following set of linear functions, right? These are going to be the degrees of freedom that define our projection. So the linear functionals do the following. They take a certain function on our function space, and basically they return the integral over the whole domain of the alpha derivative of the function, where this alpha is a certain multi-index, right? And here we are considering multi-indexes or derivatives of order less than r, where r is the degree of the polynomial space. So as I was saying, these functionals define degrees of freedom, right? Which means that if I specify this, it's easy to see that if I specify the values of all of these integrals, right, for a certain polynomial of degree r, this completely determines what the polynomial is, right? this is because they are all independent. So these functionals are all independent from each other, and they have the exact amount. So they form a base of the dual space of the polynomial functions. So specifying the values that these linear functionals take on any function here completely determines what the function is. So as I said before, this helps define a certain projection operator, right? That for any function u on our sublab space where the solution to our problem will live, we can project that down to just a polynomial space of finite dimension, right? Or polynomials of degree r. And the way we do that is as usual, as is done, for example, with nodal evaluations on the Lagrange finite element space. Here we do it in this way. We just require that these linear functionals match, right? So how do we define the projection here? If I have a certain function u, how do I define its projection onto the polynomial space? Well, I just require that each of these degrees of freedom have the exact same value as the when they are evaluated on the function itself, right? So this, as I was saying, just specifying the values of the degrees of freedom on a certain polynomial completely determines the polynomial. So this defines the projection. If you give me any function u, this will give me, I can give you the projection onto the polynomial space by specifying, by just calculating these values here, right? And a very useful property that this projection has, which is basically the reason that we're going to use it now, is this kind of commutation property that they satisfy. Essentially, if I take the beta derivative of the projection of a certain function, this is going to be the same as the projection to a smaller space, right, of polynomials of degree r minus order of beta of the derivative of the function, right? So essentially, if you look at this, we have a certain kind of computation that first taking the derivative and then, first projecting and then taking the derivative is the same as first taking the derivative and then projecting, but now to a reduced polynomial space. It is easy to see that these two things match because they are both polynomials, right? They both live on the finite dimensional polynomial space because we are projecting here, and derivation is closed here in the polynomials. And so basically we are comparing two things that live on the polynomial space. And it's easy to see that if we evaluate the degrees of freedom on each of these, they have to basically be the same. If you take the alpha derivative here, you're going to get an alpha plus beta derivative of this projection, which by definition is going to be when you integrate it over the domain, is going to be basically the alpha plus beta derivative of the function itself, and the same here, right? When I take the derivative of this projection, again using the definition here, it will tell me that it's the same as the derivative of the function that I am projecting here. So I will end up again with the alpha plus beta of u. So essentially, by definition, these two things are the same. And this is a very important property that this projection satisfies, which is going to be very useful again for the bounds that we are going to construct in a moment, which is and before, sorry, just a earlier interpretation of what this kind of projection gives. If you think of the Taylor polynomial of a certain function, we can think that this TR of U gives the Rth Taylor polynomial, right? So we have a certain TR operator acting on this function, which returns the Taylor polynomial. And how is the Taylor polynomial defined? If you remember, probably going back to your calculus classes, very likely you defined it in a very similar way, although probably you didn't state it in this way. But the idea is that you are basically trying to match the values of the derivatives, right? So this is evaluated at a certain point. So this is a way of saying that, right? We define the Taylor polynomial here by demanding that its derivative evaluated at the point x0 coincides with the derivative of the function itself that I am trying to get the Taylor polynomial of when I evaluate it at x0. So here we are essentially doing kind of the same thing. We are matching now, instead of the derivatives evaluated at a point, we are matching the derivatives kind of averaged on the whole domain, right? But the idea is basically the same. And it works for the same reason, because the dimensions are right. So in a way, we can say that this projection here gives a sort of averaged Taylor polynomial, right? So yeah, this is just to get some intuition of what this is. And now, finally, I introduced the Bramble-Hilbert lemma here, which is an important result that we are going to use now then to build bounds on a mesh, right? So the theorem says that given a certain domain on Rn, Lipschitz domain, and R is a certain non-negative integer, then there is a constant C, again depending only on the domain and of course on the integer here, that satisfies the following inequality, right? And this inequality says that if I take polynomials in our polynomial space and I look for the one that minimizes the Sobolev norm of order R, so the Sobolev distance to a function, then this can be bounded by this constant C and the HR plus 1 semi-norm of U. And here, this I should clarify why I'm using a different symbol here. As you can see, instead of 2 bars, it's just 1. And why I say semi-norm instead of norm. Here with this, I mean, if we go back, I should have put this in a slide, but let's go back to here. Instead of considering all of the derivatives for the norm, we just integrate the derivatives of higher order, right? So that doesn't give a norm because it's not necessarily positive definite, right? Because it can easily be 0 for functions that are non-zero. So that's why we call it a semi-norm and not a norm, and use a different symbol. Oh, sorry. Yeah. So now this provides a very useful bound because it tells us on a given domain how close we can get with polynomials of degree R to a certain function that has this regularity here, lives on the Sobolev space of degree R plus 1. And this is the kind of thing that we need. So yeah, for the proof of this, it's based basically on the property of this projection operator that we just defined, and on the Poincaré inequality that I showed you before. And it's a constructive proof. So this is the reason I introduced the projection first, so that now basically, if we go back to the statement of the theorem, we are going to construct a certain projection that gives a specific polynomial that satisfies this bound here. So essentially, we are constructing we are giving a constructive proof. And this is what the projection operator that we defined is useful for. So let's see how it goes. Let's take a function with this degree of smoothness, right, in this sublet space of order R+1, and now define its projection to the polynomial space as we did before. So now we know that by construction of this projection, we have this property here. Sorry. The integral of the derivative here of this difference has to be 0 for all derivatives of order less than R. And this is essentially by construction, because this is what we demanded. We demanded that the derivative, the integral of this derivative matches the integral of the derivative of this term here. So of course their difference is going to be 0. So this thing has 0 average for all derivatives of up to order R, right? So these are the conditions that the Poincaré inequality requires. If you remember from here, we're going to use this inequality here, right? Because we know that the average of the function is 0 on our domain. So we are allowed to use the inequality. And what the inequality gives us in this case is that the L2 norm of the difference between the function and its shadow on the polynomial space, right? Its projection on the polynomial space is less than or equal to C1, where this C1 only depends on the domain, and basically the sum of the L2 norms of the derivatives of order 1, in this case, of this function of order 1, because remember we were bounding the L2 norm of the function with the L2 norm of its gradient. So this is another way of saying the same thing, basically. And here we have used the commutation property that we introduced before. When I take the derivative of this thing, is essentially the same as projecting to polynomials of degree R-1, the derivative of the function, right? This is by definition of the projection. We know that this property holds. So now we can look at this thing here and notice that in a way, it looks very similar to this thing here. So this is what I put first step here. We're going to be doing recursion. If we identify the alpha u with u, we can say that we can see that this thing here has the same form essentially, where now the derivative lives on the sublet space of order one less order. So we can again apply this result here, but now to each of these terms, right? So then what we find from that, this is what I was saying. What we find from that is that we can bound the L2 norm of this difference here, but now by derivatives of higher order appearing here, right? We have now the derivatives of order 2, and we have again this difference of the derivative of order 2 of u minus now the projection of 1 less degree, so onto polynomials of 1 less degree than the one we had before, so 2 less degrees than r, of the derivative of the function u. And again, we have the same form here, so you can see where this is going. We can apply this, continue to apply this recursively, and after r+1 steps, what we're going to have essentially is that this projection will disappear, because we are going to be projecting onto 0, because we are going to get degree 0, and so we are going to be projecting things of degree 0, so that will be 0. And essentially what we're going to find here is that the L2 norm of this difference can be bounded by a certain constant C that will come from the, all the products of these different constants that the Poincaré equality gives. But this doesn't really matter. We just want to know that it's a constant that doesn't depend, that only depends on the domain. And we're going to have here then the sum of all the derivatives of the highest order here up to order r plus 1, right? So essentially, yeah, this is a result, right? But again, we can apply this same result now to the derivatives themselves, right? And this is what we can do here. The derivatives live on this less smooth Sobolev space. And essentially, if we apply the result before, we can bound the norm of the derivative minus its projection onto the polynomial space by this constant C. And now the derivatives here of order r plus 1 minus the order of beta here, right? Where this is the gamma here. So essentially, this is like taking the alpha derivative of u of order r plus 1, right? Because beta, so r plus 1 minus beta plus beta is essentially r plus 1. So now for the derivatives, we get this result here as well. So putting everything together, let me go back. We have this bound here, bounding u minus its projection by a sum over the derivatives of order r plus 1. We have the same for the derivatives of u minus its projection, again bounded by the same thing. So if we sum everything together, on one side we get the Sobolev norm of order r plus 1, of order r, and on the other side we just get basically the semi-norm. So some kind of constant times the semi-norm, which was, if you remember, just considering the derivatives of highest order here, the semi-norm of order r plus 1. So this is essentially a constructed proof of the Bramble-Hilbert lemma. We constructed, if we go back to the lemma only says, okay, there is, so that by approximating with polynomials in this polynomial space, I can get as close as a constant that only depends on the domain and the r plus 1 semi-norm of the function, right? And the way we prove that is we found a given polynomial. Where is this? Here. Given polynomial, which is this projection here, that satisfies this inequality. So that proves the lemma. And one important corollary that can be deducted from that lemma is the following. And the idea of this corollary is that we want to get rid of that projection that I introduced before, which is based on somewhat abstract degrees of freedom. So it's sort of an average Taylor polynomial, but it can be, a little abstract to reason in terms of that, and it's not what one uses in practice. So in a way, okay, we use that as a tool to prove the Bramble-Hilbert lemma, and now we're going to use that lemma to get rid of that projection and basically use any projection that we want, like, for example, the ones that we use for defining the Lagrange finite elements or anything else. So essentially, this corollary is a generalization where of the Bramble-Hilbert lemma, where now this projection can be any projection that satisfies certain properties. So this is the corollary. Omega is a certain domain, again, a Lipschitz domain. And this projection here that we take from our function space subwave space of order r plus 1 to the polynomials of order r, we ask that it be a bounded linear projection, right? So then we can guarantee that there is a constant c, which depends only on the domain and on r, and in this case also on the norm of the projection, such that this property holds here, which is essentially the content, or it is very similar to the Bramble-Hilbert lemma. We are saying that the norm of this error here that we get by projecting the function u to the polynomial space, measured in the Sobolev norm of order r, is less than constant that only depends on these things here, times the r plus 1 semi-norm of u, which considers the derivatives of u to one higher order. Yes. Did someone want to say something? I heard something. Okay, if not, I'll continue. So yeah, and the way we can prove this is very simple, luckily. And of course, using the lemma that we proved before, we basically take any function here in this Sobolev space, and we take any arbitrary polynomial in our polynomial space. And so we can see that this difference here that we're trying to bound can be bound in the following manner. Basically, we subtract the polynomial p here, that is any arbitrary polynomial for now. We know that it has to project to itself because pi is a projection. So it has to be basically the identity when restricted to the space that it's projecting to. So essentially here we are subtracting and summing p. So this has no effect. So this is essentially, here I put less or equal done, but it should be an equal. This is essentially equal. And now we can use the triangle inequality that holds for any norm by definition, and get the following bound here. Essentially, we take this on the one hand and this on the other hand, and this term here can be further bounded by essentially the norm of the projection pi times the norm of u minus p. So what we have in the end is essentially 1 plus the norm of the projection pi times the norm of u minus p. And the reason, this thing appearing here is the reason why the constant in the corollary also depends on the norm of the projection itself. It's still good enough. So now so far p is arbitrary, right? So this is true for any arbitrary polynomial here. But now if we take the infimum of this thing over all of the polynomials that live in this space, we can apply the Bramble-Hilbert lemma basically to conclude that this has to be less than or equal to a certain constant times this factor here, and times the semi-norm of the function u, right? Because by the proof of the Bramble-Hilbert, we constructed a polynomial that satisfies this, right? So yeah, so that proves the corollary. And this, going back to the corollary, I put a box here because it's a very important result. This is what we were trying to get to, and this is what we are now going to apply to our mesh. And yeah, the way that we are going to apply it to a mesh is not completely straightforward, right? It's not that we cannot take, okay, the mesh is our domain, and because on each triangle we have a different polynomials, and also we cannot directly apply it to each of the triangles of the mesh, because then the constant in the corollary will depend on each of the individual triangles, and that will make it difficult to obtain a global estimate, right? So we need to construct a certain way of talking generally about all of the triangles first, in a
Joaquin,
way. Yes.
want to make a poll?
Okay. Yeah. Sounds like a
A good.
yeah. Okay.
Let's
So
say
when should we? Yeah.
maybe at 11:40.
It sounds good. Yeah. Sounds good. Yeah. 40 maybe. Yeah. Yeah. Okay. Yeah.
Ready?
Okay. Wait a second. Yeah. So, okay. Yeah, that was indeed a very good place to pause, because if you didn't get anything from the first part, which is frankly possible, I only want you to take this result away for the second part. This is essentially the only thing that we need uh, for the estimations that we want to do in the second part. So far we did everything in a rather abstract setting, let's say, on some Lipschitz domain on our end, and now we want to use this to make estimations on for finite element approximations with respect to a given mesh. So let me just recap what this result was saying. So we are this U here is going to be the solution to the problem that we're trying to solve. We are going to have a certain polynomial space on a domain where we are going to interpret this domain omega as each triangle of our mesh. And now we're going to see how we can do that. And then this polynomial space is going to be essentially the polynomial functions that constitute our finite element space, right? So then we're going to have a certain projection, which is going to tell us how we can represent any function on this solution function space, how we can represent that in terms of something smaller, something manageable by a computer. That's why we want to do it, which is finite dimensional and lives in this polynomial space. So this projection will, for example, in the case of Lagrange finite elements, give us what the representation is in the Lagrange finite element space of a certain function. And what we want to know is how well we can do that, how well we can approximate our solution function by this projected function to our finite element space. And what we found here is that we can bound this approximation error, let's say, then by a constant c that depends only on the domain, on the degree of the approximation that we want to do, and on the norm of the projection that we are talking about. And times then the r+1 semi-norm of the function that we are trying to approximate, right? So as I was saying, then we're going the way we're going to use this result is by interpreting this omega as each triangle of our mesh, and then putting everything together to get an estimation on the whole mesh. And in particular, what we want to know is what this constant c is when we, instead of having some general domain, now we say, okay, we're talking about triangles on a mesh, right? So we have, we want to know how this constant c depends on the properties of those triangles, in particular on their size, and other properties that I'm going to mention now. So this is what we are going to do now. We are going to try to apply these patterns to the case of a mesh. There is some, yeah. Okay. So, and as I was saying, we are going to interpret this omega as a triangle on our mesh. But as you probably saw, I think from the examples, applications from the numerical part of the course, these triangles are not equal to each other. This mesh is not necessarily uniform. These triangles may be very different, may have very different properties. So this bound, in particular the constant that enters in the bound and depends on the properties of the domain, may well depend on the properties of each triangle. So in principle, it would be difficult to put everything together if nothing has anything to do with each other. What we first need to do is to construct a certain kind of dictionary, let's say, or mutual language to speak about what the bound is on any given triangle in terms of some common reference frame. So this is what we are going to do now. It sounds more difficult than what it is, but essentially the idea is to think of a certain reference triangle and apply the corollary. So this thing here, apply it to our reference triangle, and then see how these bounds translate when we map from our reference triangle to our actual physical triangle on our mesh. So we want to build first, let's say, a common language that that tells us what the bound is for the given reference triangle, and then we want to build a sort of dictionary that tells us, okay, how do the norms transform when I go to the from the reference to the actual triangle, and how the derivatives change, and so on. So essentially, this is the program for the second part of the class here. So let us start then with building this reference triangle, which is simply just a triangle with three vertices on these points. So basically on 0, 0, on 1, 0, and on 0, 1. So a very nice a reference triangle. And we're going to define, we're going to start with a simple projection, right? We're going to take polynomials of degree 1 on this reference triangle, and the projection that we're going to build, or that we're going to be working with, is the basically the linear interpolant. What does this linear interpolant do? Well, it basically gives a certain, so it takes a function u, and it gives a projection, which is called the linear interpolation of u, which is a linear polynomial here, that essentially evaluates to the same values on the vertices of the triangle, right? So this is the way we define the linear interpolant. And one thing that we have to see if we want to use this for the corollary of the Bramble-Hilbert lemma is that this operator is bounded. And this is relatively easy to see if we take here the norm of the linear interpolant applied to a certain function u, we see that this cannot be any larger than the norm of u itself. And this is because this being a linear polynomial, it must attain its extreme values at the vertices of the triangle. And the vertices of the triangle is exactly the places where it coincides with the function. So it could never, so the norm of this function could never be larger than the norm of the function itself, right? And then again, this by the Sobolev embedding, this is a property that I think you probably saw before in the course, but essentially we can say that this L infinity, so this the supreme value of u is bounded here by the H2 norm of u, which essentially lives inside the continuous function space. So so yeah, so we're saying we can say that this interpolation is a bounded linear projection. So we are enabled to use the result of the corollary. And what the corollary says in this case is that the error that we make by approximating the function u with its linear interpolation can be bounded in this case by the H2 semi-norm of the function on the reference triangle. And this is essentially the key bound on the reference triangle. And what we want to do is now see how we can translate this to all of the arbitrary triangles of our mesh. So we essentially want to see how the norms transform here. So let's start now by looking at how we map from a reference to an arbitrary triangle. So we have this here, the reference triangle with its vertices v0, v1, and v2 hat. And this is our arbitrary triangle. It doesn't have the same shape. It can have different shape. And this is the triangle that actually lives on our mesh, on our triangulation. And we know that there is a mapping between the two. In particular, that there is an affine mapping, which is essentially a linear transformation and composed with some translation, right? This is what an affine map is. So yeah, so we're saying we know that there is such a map, not only that there is such an affine map, but this map is also unique. And what this map satisfies, well, essentially we can define it in this way. It's a map that takes each of the vertex and maps it to the corresponding vertex in the arbitrary triangle. And it's simply given by this expression here, what the map takes any point in the triangle, and it basically multiplies by a matrix B, which is this matrix here that I'm going to show, and then translates by B0. And this matrix B here can be simply given by, so this notation here means that we have V1 minus V0 as a first column and V2 minus V0 as a second column. So this is essentially, if we think we are in a R2, so this is essentially a 2 times 2 matrix. And now we want to see what the properties of this map are, so that we can translate our bound from the reference triangle to the arbitrary triangle. So first, we can see that the determinant of the linear part here of the map is essentially 2 times the area of the arbitrary, let's say, physical triangle. And this is because the area of the reference triangle is simply 1/2. And the way that the area is transformed by an affine map here is by this factor here, the determinant of B. So necessarily for these two facts to match, the determinant of B must be equal to 2 times the area of the physical triangle. So now we want to see how to translate information about functions, right? So let's imagine, so we have our reference triangle here, we have our physical triangle here, we have our affine map that basically goes from the reference triangle to the physical triangle. And now let's imagine that we have a certain real function that lives on the triangle, right? So for each point on this triangle, it evaluates to some point on the real line, so some real number. And we want to translate this now to the reference triangle, right? So this is essentially what's called a pullback, and it's rather simple. And essentially, if we know how to go from the physical triangle to the real numbers, and we also know how to go from the reference triangle to the physical triangle, we trivially have a way to map the reference triangle to the real numbers, right? Which is essentially by the map composition. And this composite map is what it's called the pullback, right? It's like I'm pulling back, I'm bringing this map F, I'm pulling it back via this big F to the reference triangle, right? To get now a real function, but now on my reference space, my reference triangle. So to put that in more concrete terms, we define again the pullback, like we said, as the composition of the two maps. So this little f is the real function on the physical triangle, and we have the f hat that is essentially defined as the composition with the affine map that takes the reference triangle into the physical triangle, right? So if we now want to know how the derivatives translate between one space and the other, we simply use the chain rule, and we obtain here, as expected, just the coefficients of the linear part of the matrix, which is the affine map, which is the Jacobian essentially of the transformation. So and similarly for higher order derivatives, we can get analogous expressions here, whereas the higher the order of the derivative, then the higher the degree of the, so the more factors involving components of the matrix B appear. So what we can obtain in general here is a bound of the following form. Here I'm using this handy notation for derivatives of arbitrary order. And here, so if we sum over derivatives of order R, we can bound this by a certain constant C times here the norm of the matrix B. This will come from the components of the matrix that appear when we take the transformation, and here the exponent R appears, which corresponds to the order of the derivative that we are taking, and all of that multiplied by derivatives of the same order here, but now of our function f living on the physical triangle. So this gives us a bound of the derivatives of the function on the reference triangle in terms of the derivatives of the function on the physical triangle. And we can do the same thing, but the other way around, to bound the derivatives on the physical triangle in terms of the derivative on the reference triangle. But now we have the So the reasoning is the same, but the mapping is the inverse. So we have here the bound of the sorry, the norm of the inverse of the matrix B. So now what we want to do is to bound this norm of B in terms of the geometric properties of the triangle, right? Because this will lead us to know then how the error bounds for the approximations depend on the properties of the triangle. Ultimately, they will come from here. So to do that, there are two key properties of the physical triangle that we have to look into. One is rather simple. This HT is the diameter of the triangle, right? Which is it's nothing else than the longest side of the triangle, right? Is the maximum distance that 2 points can be apart within this triangle. So that's the diameter. And also we want to consider here the inscribed circle on the triangle, which is this circle here. And in particular, we want its radius, right? And I'm going to explain in a moment why this is important as well. Which is in a way maybe less intuitive why this comes into. But yeah, so as we say, we want to bound the norm of B and the norm of its inverse. So the norm of B is rather straightforward. Essentially, we know that B has as columns the difference of the vertices of the triangle, so they cannot have length longer than HT. So that norm has to be bounded by HT, right? The diameter of the triangle or the length of the longest side. So this simply bounds the norm of B. But we also need to bound the norm of the inverse. So that's why we introduce this diameter. And to see what the problem is here, why we need this quantity. So B is the map that goes now from the physical triangle to the reference triangle here. So you can imagine that if this radius here is too small compared to the diameter. So if we have a very thin triangle, which is something that we usually don't desire in this kind of approximations. Intuitively, it's easy to imagine, but the mathematical reason why this is required will come up here in a moment. So if you imagine now you have a very thin triangle where this radius is very small, B minus 1 might take 2 points that are very close to each other on opposite sides of the triangle, but since the triangle is very thin, they might be very close to each other, and we'll map it here to the reference triangle, where now those points get far apart. So the norm of the inverse matrix could be quite large, right? If this rho t is quite small. So this is another parameter that we want to control, and that allows us to control the norm of b to the minus 1. So this is the reason why I introduced this parameter. And to see how it bounds the norm, now let's go back here. So to see what the norm of a map is, we want to see how it maps a full circle, right? So take any direction and see what it does, right? So we want to take a certain fixed length, which in the definition of the norm of a map of an operator is usually taken to be 1, but it can be anything. It doesn't matter what the exact value is. So now we have a full circle within this triangle, and we want to see what this map does to any point within this circle. And the reason is that since we are covering all directions, we know that then we can write the difference of any 2 points. We can, any vector of length rho t, we can write it as the difference between 2 points on this circle, right? and those 2 points live within this triangle, right? And to see what the inverse map does to those points in that circle, essentially we know that b minus 1 maps this triangle here. So any 2 points that live on the circle cannot be mapped further apart than the square root of 2, which is the diameter of this triangle. So that gives us a nice bound to what the norm of the inverse map is in terms of this radius, right? Because it's mapping vectors of length rho t at most to vectors of length square root of 2, right? So basically, we can bound the norm of the inverse matrix as less than the square root of 2 divided by the length of the inscribed circle, the radius of the inscribed circle, right? And this factor here doesn't really matter. What we want to know is just how this scales. This is what I was saying, how the bounds here will depend on the properties of the triangle. So we have this one here, which depends on the diameter of the triangle, and this one here, which depends on the radius of the inscribed circle. So intuitively, what we're going to want is, okay, for sure we're going to want small triangles. So we want to have small diameters of the triangles so that our mesh is sufficiently fine and it allows for an accurate approximation. But not only that, because we don't want ugly triangles, like thin triangles. In a way, we want them to kind of go uniformly, rather similar to each other. We don't want them to be weird. So we also want to have a certain bound of this radius in terms of the diameter, right? And yeah, taking our bounds for the derivatives that we did before here, now is just putting the values here, the bounds for the norm of b. We can write these expressions here. We can bound the derivatives of the function in the reference triangle by a certain constant times the diameter of the triangle to the r, and multiply by the sum of the derivatives here of the order r, and the same for the other way around. Now, when we use the inverse map, now we have to use this bound here in terms of the radius of the inscribed circle. So yeah, this gives us a way to map derivatives from one to bound derivatives on one side in terms of the derivatives on the other side. And this is we're going to see why it's useful, because in the end, like I said at the beginning, we want to know how the norms map from one triangle to the other, because we have a nice bound on a reference triangle, and we want to bring that to a bound on the physical triangle, which, as expected, will depend on the properties of the physical triangle. And here we're clarifying what the dependence is. So yeah, if we have any function f on the physical triangle, we can write its L2 norm in this way. This is just the definition. And if we change variables here in the integral, simply, we can write this as the integral now on the reference triangle, and where the factor that appears here is just the determinant of b. And that we saw that it was equal to 2 times the area of the reference triangle. So now we know that how the norm of a function is translated from one side to the other of the mapping. Essentially, we have that the norm here is the square root of 2 times the area of the triangle times the norm in the reference triangle. Now we want to do the same for the HR semi-norm. This is again to bring the corollary to the Bramble-Hilbert lemma to use now on every triangle. So again, rather straightforward, a little bit messy, but still straightforward. We can write this semi-norm here as the integral of the derivatives of order beta, sorry, of order r, And using the bounds that we found before for those derivatives, we get a factor here of the rho times rho to the minus 2r, right? Where r is the order of the derivative that we are taking, and times the sum over the derivatives, but now in the reference triangle, right? Now, if we change variables here again, we get the factor 2 times the area of the triangle. And so we can, yeah, we get this factor out here. And now the integration is done over the reference triangle. So after all, we get this expression here in terms of the area and the radius of the inscribed circle and the norm of the pullback, right, of the function on the reference space. So after all, cleaning up a little bit, we have this bound here, and just doing the same thing but with the inverse map, we get an analogous bound here, where now the factor of t here appears to the minus 1/2 because we have the inverse map. And again, now instead of the rho, we get the diameter of the triangle, right? So now finally we are able to translate our bound coming from the corollary to any triangle, right? And let's see how we can do that concretely. Let's take a certain function on H2 of the triangle, and let's call U hat to its pullback to the reference triangle. So then we get essentially this bound here, right? So this, yeah, this we know, and this was the reference triangle estimate that we had before. And if we want to bring that now to the physical triangle, we just have to notice that this thing here is the same as the pullback of this thing here, right? And that's because both the interpolator on the reference triangle of the pullback of the function and the interpolant of the function in the physical triangle, they both are linear functions, and by construction, they because of how the pullback is defined, we know that they are equal to u evaluated at VE at each of the vertices of the reference triangle, right? So necessarily, since they have the same values on the vertices of the triangle, they have to be the same thing because they are linear. So essentially, we have this relation here. So knowing that this is just the pullback of u minus ITU, and knowing how to translate a norm on the reference triangle to the physical triangle, now we finally can get can transfer the error bounds now to the physical triangle, right? And yeah, that is simply done in this way. We want to calculate this thing here first for the L2 norm, u minus ITU, and this we can bound just using the result before by c times the area of the triangle to the 1/2, and the L2 norm of the pullback of this thing here, right? This is the way that the norms were mapped. And finally, using the corollary here, we can obtain this bound here, right? And finally, for the H1 semi-norm, we can do the same thing. It's essentially the same logic, and we get now a bound here that depends on HT and on also the quotient between HT and rho t, right? And so this gives us finally then all the information we need to put bounds on now the whole mesh. So yeah, let's see how we can do that. We have done before, here we're just tidying up, is just prove the following theorem. If we define the shape constant as the quotient of the diameter of the triangle and the radius of the inscribed circle, this is the thing that we more or less want to bound, right? We don't want this to be too small, right? We don't want the triangle to be too thin. So I mean, sorry, the other way around. We don't want this to be too big for the triangle to be small, too thin, sorry. Yeah, putting everything together, what we have proved is this theorem here, that there exists an absolute constancy such that the L2 norm of U minus its linear interpolant is bounded by this constancy and times the square of the diameter of the triangle and times the H2 semi-norm of U. And on the other hand, if nothing, basically we know that there is a constant C prime, but now that depends on this shape constant. That allows us now to bound also the H1 semi-norm in this way. This is what we saw before. Well, C prime, now we can see that the factor just disappeared. We absorbed it into the constant here. So we have the HT here. And so yeah, now finally, so this is the result essentially of the corollary applied to the physical triangles, individual triangles of our mesh. And now we are finally in a position to put everything together, just simply adding over the triangles. So which is the constant, the content of this theorem here. Let's say that TH is a certain sequence of triangulations of omega. We want to know how much better the approximation gets as soon as we make the triangulation finer in general. So we are saying that the mesh size here, that remember was the diameter, the largest diameter of a triangle on the mesh. We assume that this thing goes to 0 for this sequence, so we are getting finer and finer triangulations. So then for a continuous function on the domain, we call this just the continuous piecewise linear interpolant, right? So before we were talking about the linear interpolant on each triangle, and now basically we just extend that to the whole mesh trivially, just doing the linear interpolation on each triangle, and of course with proper conditions, so that is done in a continuous manner, so that the result is continuous. And we call that the continuous piecewise linear interpolant. So then we know that with these conventions here, there exists an absolute constant C, such that this approximation error in the norm L2 can be bounded by C times H squared and the H2 semi-norm of U, right? And this will get smaller and smaller, and it will be getting so the bound will be getting better and better with a convergence rate 2 in this case. And also, if the triangulations are shape regular, so remember going back to the single triangle theorem, we had that this C prime depends now on the shape constant of the triangle, this quotient here. So assuming that the sequence satisfies a certain goodness condition of behavior, which is essentially that we can bound this shape constant uniformly. Then there exists a constant C prime, which only depends on this uniform bound that satisfies the following. We bound the H1 seminorm of the error by C prime times H. Here, instead of H squared, we have H, and the seminorm of U. So this we constructed for the linear interpolant, but it can be done in the same way for other interpolants to other higher degree polynomial spaces. I'm not going to go into the details of how that is done, but essentially it's the same idea. It's apply the corollary and map from the reference triangle to the physical triangle and add everything together. But the result that we get in the case of the Lagrange finite elements of degree R is the following. Now the L2 norm of the approximation can be bounded by a constant C times H to the S here, where S is the order of smoothness of the function, and of course here it's bounded by the R plus 1, where R is the degree of the polynomial space, and the HS semi-norm of U, right? So going back to this, here you can see the relation. We have polynomials of order 1, linear polynomials, and we have a convergence rate of order 2. This is the same that we get here. So and the constant C is absolute, right? And finally, if the mesh is shaped regular, then we can also apply the other bound in very much the same way. And for the H1 seminorm, and here we get a convergence rate of 1 less degree than for the L2 norm. So yeah, few remarks. So if U is smooth, so in this case, in the R plus 1 sublet space, the convergence rates that we get from that theorem are H to the R plus 1 and H to the R for the H1 norm. If U is less regular, so if S is smaller, then we will get a correspondingly reduced convergence rate. And on the other hand, we are limited to these convergence rates, essentially because the interpolant is exact on polynomials of degree R, but not on higher degree polynomials. So we cannot do better than R plus 1. So finally, shortly, a few applications to the Dirichlet problem of these bounds. Let's take a Dirichlet problem like this. The divergence of A times the gradient of U equals a certain function f in the domain. And we put Dirichlet boundary conditions so that U vanishes on the boundary. And this function A here, this coefficient, we assume that it's bounded above and below by positive constants, and that this inhomogeneity here is in L2. So then the weak formulation of this problem essentially can be put in this form. This I think you have also seen before. Just a little recap. Essentially, the weak formulation of the problem is trying to find a certain U in the sublet space that vanishes on the boundary, such that this form, the linear form B here, applied to U and V for all V equals this function here, where B is this bilinear form here, and F is this function here. So you can see that this is the weak formulation of the problem here. And this symmetric form here has nice properties. In particular, it's bounded. We know it's bounded. So the modulus of the form applied to any two vectors can be bounded by some constant m, which equals the supreme of the coefficient a, and the h1, the product of the h1 norms of w and v. And also we know that it's coercive. This comes from Poincaré's inequality, and essentially it allows us to see that indeed b applied to v and v is bounded by a certain constant, positive constant gamma times the square norm, h1 norm of p. So that means the symmetric form is coercive. And now, yes. So now we want to see how well we can do by approximating the solution to our problem in a finite element space. So we take a certain space here to be the Lagrange finite elements of degree r with mesh size h that vanish on the boundary, right? And let us assume that u here is the solution to the weak problem, which is the function that we want to find, and assume that uh here is a finite element solution. So the best approximation that we can do by our finite elements, and which is defined in this way here, which is essentially using the equation. Going back here, the equation tells us that b of uv equals f of b for all v in v. And now instead of looking at the whole space, we just look for v's within our finite element space, and that we can do because everything is finite dimensional. So we look for the UH that satisfies this property here. And this was proven before already, that the approximation error for this finite element solution also can be bounded here by a constant c, and the infimum of all of the functions within the finite element space of this norm here, where this constant c is 1 plus m, where m was the supreme of the coefficient a of the equation, and this gamma is the constant of coming from the coercivity of the bilinear form. So here we're just going to use this, but it shows how important the property of the properties of the function b are. So yeah, basically, if we apply the approximation results that we obtained here, essentially this translates to a bound on the norm here of this form, where h is the mesh size, and it's raised to the power of r, and we have here the r plus 1 norm of the function u. So yeah, as I was saying, the ability to control the error here comes from the coercivity of the form. But on the other hand, the approximation rate that we get, this power of r here, comes from the finite element approximation theory that we developed here. Finally, we want to do some estimates now in the L2 norm. In particular, we want to know how a certain functional can be approximated by the finite element solution. So for example, I don't know, let's say we have a mass distribution and we want to know the center of mass or something like that, where U is the mass distribution, and this thing will be a functional that calculates the center of mass, in particular where G here would be X, that would allow to calculate the center of mass. And So typically we will be interested in functionals like this to extract. So we not only want solutions to the equations, but we want to know their properties, and these properties are generally expressed in terms of these functionals. So we also want to know how well we can approximate the functionals themselves. And it turns out we can do quite well. So let's take a given G in L2 here that defines the functional in this way. And let's see how well we do when we approximate by the finite element solution. So first, we do a little trick. We define the trial function relative to the functional G in this way. It's very similar to how the weak problem is set. We're going to see that a little better now. But essentially, when we define the trial function phi on V as the function that satisfies this property here, which is similar to the problem that we are trying to solve, but instead of F, we have G. So essentially, we are looking for the solution of an auxiliary Dirichlet problem that's essentially this similar to the problem that we initially had, but where we replace the function f by the function g. And the boundary conditions are the same. So this defines our trial function, and we are going to assume that that this function is in H2 as well, and that the norm can be bound by some constant and the norm of the function g in L2. And this may seem too strict, but it's not very indeed, because it holds whenever omega is convex or smooth, and when A is smooth and bounded away from 0. So it's rather generic. So we assume this. And if we consider the error now in the approximation, the functional evaluated on the function u minus the functional evaluated on the finite element solution, this by definition we can write in this way, which is essentially also by definition b applied to u minus uh times phi. This is by definition of the trial function. And here we have another property, which is the Galerkin orthogonality, that tells us, so we know that this approximation error lives outside of our finite element space, because if it lived inside, then we wouldn't have the best approximation. So we know that the error is outside. So Galerkin orthogonality tells us that this vector that is outside has when I evaluate the symmetric form on on this vector outside and any vector that it's inside, that has to be 0. This is what Galerkin orthogonality says. We kind of think of B inducing some kind of dot product, and then this dot product between anything outside the finite element space and anything inside will be 0. So we are free to just add here or subtract any vector in the finite element space, because we know here the form is linear. So the form applied to u minus uh and v will be 0. So we are free to do that, and this allows basically to bound the error like this. We have the absolute value of the error. It can be bounded by the constant m, and the norm here h1 norm of the u minus and the infimum of this norm here, where v spans over all the finite element space. This comes essentially from the boundedness of the symmetric form here. So this allows to go here. And finally, from the theory that we just developed, we know that this thing here we can bound it by c times h, where h is the mesh size and the h2 norm of phi. And we assumed that this can be bounded in this way. so that phi can be bounded by G. And so after all, we get that the approximation error is bounded by C prime times H times the norm of U minus UH times the L2 norm of G. And using the previous results, then we finally can write this bound here, that C times H to the R plus 1. Sorry, that this error here is less than C times H to the R plus 1. And now here the R plus 1 norm of U and the L2 norm of G. So yeah, just as a comment here, again, we can see that if we, as we assume G is in L2, then the error for this is of order R plus 1, which is 1 power of H higher than the H1 error of the approximation to the solution. And finally, then we can extract some more useful information from this if we consider the very important special case where G itself is the error of the approximation. So then basically we can just use the result from the previous slide to, after all, write a bound for the L2 norm of the approximation like this. So as you can see, the L2 error in the finite element method then will converge here with a rate of R plus 1, which is 1 power of H higher than the H1 error. And that's all that I wanted to tell you today. So yeah, if you have any questions, just let me know.
Nice, really nice. Are there questions? There? Sí. Well, hey, thank you
Okay.
then. We continue to
Yeah. Okay. All right. Thank you. Bye.
Joaquin,
Wait.
that's parency. This is the same result that before, right? But
Uh,
different. Either the normal two of the
Let me see. Yeah. But now, yeah, let me think. So well, we knew that if U is smooth enough, then it's order R plus 1. But yeah, you're right.
Okay, so
But did we know what the bound was? Yeah, it's sort of a consistency check, I guess. Yeah, that is true indeed. Yeah, it's another way of obtaining the same thing, which I didn't realize.
sync.
Yeah.
I think 7 will.
Yeah. Yeah. Okay. All right. See you. I think I am the host, so I would end the meeting. Okay. All right. Bye bye.